Okay, this one. Oops, too much. There we go. Okay, so a completely irrelevant, a 12-pack of Omni Cola, whatever. So basically a box with a mass of 4.3 kilograms. Oh, let me get the lights. Is initially at rest on a horizontal floor. It is then pushed in a straight line for 1.2 meters by a trained dog that exerts a horizontal force with magnitude 36 newtons. Use the work energy theorem to find the final speed of the box if there is no friction and if there is coefficient of friction, kinetic force, uh, 0.3. Okay, well, first one, let's sketch a quick FBD. Okay, so here it is. Okay, so okay, so if there is no friction, well, there is Fg, there is Fn. Um, Whatever you can say, you want to make it a tension here, for example, you want to make it force applied. It is completely up to you. So let's just take it easy for today and just make it force applied. So F applied, and the direction of motion is this way, of course. Okay. So what numbers do we know in the problem so far? What numbers are we given in the problem, Ahmed? We know the what? Initial speed was what? 0. What else do we know? We know the distance is sorry. Well, the distance is how much? 1.2 meters, and we know that the constant force is how much? 36 newtons. Let me just change attendance here. Okay, so use the work energy theorem to find the final speed. Okay, initially, what was the speed of the box? Initially, 0. Okay, perfect. So initially the speed was 0. Um, okay, sorry? So what's the equation that relates work to energy? Basically, it's the second definition of work. Second definition of work. Come on, wake up. Say again. Change of energy. So W equals delta E. And what's the only E relevant here? EG or EK? Does this go any change in gravitational energy? Nope. It's not going up. It's not going down. So as far as we're concerned, it's EG is always 0 because it's always as the ground. And we're going to take ground to be the reference height. Okay. So what we have to start with is this. Actually, you know what? Let me, everyone, I'm going to squeeze this diagram a little bit. Sorry, squeeze it, my bad. There we go. Because I'm going to do my calculation here for part A. Okay, so for part A, W equals delta EK. What's the equation for work? I know that this is an equation for work, but what could we replace this W with? Since we know force and distance, what could we replace it with? Yep. No, go ahead. Force times distance times. Technically, what's the cosine of theta here? It's what 0 is sorry. Theta is 0, so cosine theta is +1. So we can replace this part right here, this W with F. Of course, F applied. F applied. Delta D cosine theta equals, what's delta EK? So EK final minus EK what? Initial. But what happens to be EK initial of the box? 0, because the speed initial is 0. So you can say equals EKF minus EKI. And then you can just what? Cross the EKI out and just make it 0. Okay? Can we plug in numbers now? Absolutely we can. We know the force applied. We know the distance moved. We know the cosine of theta. And we have half m. We just need the VF. Okay? So I'm just going to set up the equation. Oops, my bad. So F applied, how much is F applied? So 36. Bless you. I'll do it in purple. 36 times. How much distance are we talking about? 1.2. and then cosine of 0 degrees equals. Put this up a little bit. There you go. Equals how much? Half. What's the mass of the box? 4.3. And we just need to find what? VF squared. Okay. Well, this is a very easy equation to solve. I just have to multiply 36 by 1.2 and then divide by the product of half times 4.3 and then square root. So if we do all that in one shot here, so let's multiply 36 times 1.2. And then what's half of 4.3? Anyone? Bless you. What's 2.15? 2 from 4 and 0.15 from the 3. So divide that by 2.15. Is that the final speed? No, that's the square of the final speed. So we need the square root of this guy. So if you square root this one, boom, that's it. We expect that the box will make its way up to a speed of 4. What's the sigma situation here? 3. Okay, so that would be 4.482, so just 4.48. So that means, sorry, VF equals 4.48 meters per second at the end of the 1.2 meter distance. Okay? Make sense? How is this problem going to change when we add friction to it? Well, what's the first thing that's going to change? Definitely. The diagram. Yeah, the FBD. The FBD now is still going to have an FG. It's still going to have an FN. It's still going to have the same F applied. All of these numbers and symbols will stay exactly the same because the mass did not change and the force applied did not change. But what we're going to add here, what force is going against it now? Kinetic friction, so Fk. Okay. My question to you is, how does that change things? By the way, question, do you expect now the box to build up to the same speed as before, faster or slower? Because, by the way, did you increase your force or is the force the same? Force is the same, which means what? If the force was bigger, you might be able to what? To build up to the same old speed or to a higher speed. But if your force is the same and now you're wasting some of it to friction, there's no way you're gonna build up to what? There's no way you're gonna build up to what do you call it? 4.48. How much are you gonna build up? Not sure how much, but definitely less than 4.48. Okay, so let's go here and let's sketch a quick FBD up here, everyone. Let's do it in black. All right. So FG, FN, still F applied. And Fk. Is the direction of motion still that way? 100%, of course. I mean, no way friction makes things bounce back. It slows them down. That's the best it could do, or stops them. So go ahead and motions this way. Well, it should be perfectly parallel. So there we go. Okay. Okay. Now, question. How are we going to... By the way, okay, question. How many forces do we have here? 4. But 2 of them are completely irrelevant. Which 2 are completely irrelevant as far as motion direction is concerned? Fn and Fg. Why? Because the direction is what? What's the angle? 90 degrees. And how much work does any force with 90-degree angle does? 0. Okay. So the only 2 forces doing work are what? Are force applied and force what? Force Fk. And both of them are acting in which way? Vertical or horizontal? Horizontal. Okay, so everyone, let's calculate the work done by each force. Let's calculate the work done by each force. So let's do W app. Okay, force app, delta D, cosine theta. I'm going to move that this arrow. You know what? I'm going to move the whole thing just slightly down. Perfect. And then move this one here. There we go. Perfect. Cosine of theta. Okay. What's the force applied? Still 36. Delta D is 1.2. Cosine of 0. How much was that? Come on. 43.2 joules. Yes. Okay. What's the other work that we need to calculate? Come on. Friction, the work done by kinetic friction. Okay. Which means, I'm just going to zoom in so you can see. Which means WK. Everyone, WK equals FK delta D cosine of theta. Do we have an equation for FK? Remember, you have to revisit things from before. What's the equation for FK? What's the equation for FK from forces? Mu K times Fn. And according to this, what's the only thing equal to Fn? Fg. Because according to Newton's laws, on the vertical, there is no motion, which means this guy has got to be equal and canceling to this one. Perfect. So mu K, sorry, Fk is equal to mu K Fn, which is itself Fg, which is itself also what? Mg. There you go. Delta D cosine of theta. All right. Let's plug this in. What's mu K? 0.3. What's mass? 4.3. What's G? 9.8. What's delta D? 1.2. What's the theta now? Friction is always with or against motion? Always. Which means what? Friction force and motion are always at what degree? Sorry, are always at what angle to each other? Come on. 0 or 180? Perfect 180. What does that tell you about that number? It must have what sign? Negative sign. Everyone, work of friction is always negative. You have got to show me the negative. Unless I ask for what? What are the 3 words in a question that you can then show in your final answer an answer that's only positive? The amount, or if I ask for the magnitude, or if I ask for how much. Well, here we're not. So it's negative what? I don't know. Let's calculate that. So I need to multiply. Obviously, this is negative 1. It's already done. So this times that times that. Okay. So it is 0.3 times 4.3 times 9.8 times 1.2. How many people got? Well, obviously, negative 15.17. So negative 15.17 joules. Okay, here's my question now. Does that, okay, so what did we say, everyone? What did we say about the final speed of the box now? Is it going to be more, equal, or less than before? Less. Yes, because this one now is going to subtract what? The work of the applied force is going to lose some to the what? Work of, exactly. The work of kinetic friction is stealing some of the what? Some of the work given by the what? By what? By the applied force. So now the equation, by the way, the equation here is still going to be the same. But instead of W just being what? 43.2, it's got to be what? The W of F applied minus the W of what? When you subtract 2 things, when 2 things go against each other, did we do that before in forces? Yeah, we did. What did you call that? F what? What is the name of the force that you combine all the other forces to get? F net. What are we doing here? Not F net. We're doing what? Work net. There you go. So that now is the big take-home message for today. As much as you dealt with Fnet before, now you don't deal with Fnet, you deal with what? Work net. The network done on the system. The network done on the system. So now W net is equal to what? Delta EK. What's W net? It's the positive from here and the negative from here. So what's 43.2 minus 15.7? Well, that's easy because 0.2 is technically 0.20. So 20 minus 17 is 0.03. So this is 0.03. And 43 take away 15 is how much? 28. What's delta EK? What's delta EK? Just like before, what's half mvf squared minus half mvi squared. But what's vi? The initial state of the box was at rest. So really, this is just what? Half m vf squared. Sorry, vf squared. So how much is vf in this case? How much is vf in this case? Definitely less than what? 4.48 from before. So I'm just gonna what? We are going to, whoops, my bad. Okay, so 28.03 divided by half of 4.3, which is 215, and then square root this guy. Come on, it's already less than what? Definitely the square root of 13 is less than 4. That would be what? 3 point something. Yep. 3.61. You cut it at the 1, so you only end up with 3.61. So welcome now to what? The work energy theorem, but with friction. Now we introduce the concept of the net force. Sorry, the network on an object. All right, let's go to the next problem. Whoa, sorry. Let me look at the other ones, just in case they are more. Yes, projectile motion with energy. Okay, a baseball is thrown from the roof of a 22-meter tall building. So it's already what? It's already off the ground by 22 meters. With an initial speed of magnitude 12 meters per second and an elevation angle of 53 degrees, 53.1, sorry, above the horizontal. Okay, so up to now, it's like a what? It's like a legit projectile motion problem. Question A, what's the speed of the ball just before it strikes the ground? By the way, can you do this problem as a projectile motion problem? Yeah, we learned how to do this one with a what? With a projectile motion equation. But we want to do it with what? What's the name of this unit? Work and energy. So we want to do it with energy. Okay. So everyone, let's sketch a diagram here. So here is my ground. Here is my building. How tall is the building? Come on. 22 meters. 22 meters. And what was the kicking speed? Like the speed at which it left the foot. 12 how much? 12 meters per second. Okay. And what was the elevation angle? 53.1. So I guess I'm just gonna sketch just like this. And would it move straight up? Like what's the eventual motion of this parabolic arc? Perfect. Goes up and comes down. Is this kind of the problem we took up in class? Yeah, the baseball big slide. Same thing. Okay, so the initial speed was 12 meters per second, and the angle was 53.1 degrees. Yeah, sure. How would I find the speed here? Because that's what the question is asking. What's the speed before it hits the ground? Raise your hand if you want to suggest a method. Anyone? The question is asking, what is the speed of the ball just before it strikes the ground? How did we do it in the big slide 2 days ago? Come on. The question is asking, what's the speed here? Come on. How did we do this in the big slide? Look through your notes. Yeah. That's exactly the same problem as the big slide. The only difference is we did not have a building there. We had a baseball bat and a small height and all that stuff. Oh, also, I did not give you an angle. Yeah. Yeah. FG? Not FG. EG. Exactly. Okay, everyone. How do you always think of energy problems like this? First of all, right here. Is it in motion? Right here. It is in motion. So what energy does it have right here if it's in motion? Kinetic. Also, is it elevated? So what energy does it have here? Also as well? Once again. So that means right here, it has how many kinds of energy? Okay. The whole time, does it still have both kinds of energy? How about right here, practically? Which energy is almost completely eliminated? Gravitational, which means which energy is completely maxed out? Because remember, how many bars do we just have to deal with? 2 bars. One bar goes down, the other one goes up. All right. So that means, okay, now that we discussed the idea, how did we do it? How did we actually? What was the first thing we did in the big slide with this one? By the way, do I know the mass of the ball? Whoa, everyone, problem. I don't know the mass of the ball. Yet I'm gonna need to get EK and EG. By the way, this is gonna be very common in grade 12 and first year. You are not given something, yet you need it to calculate the amount. How come that's possible? How come the problem doesn't give you a number that you still need to? By the way, what's the equation for EK? Come on. Half mv squared. What's the equation for EG? mgh. I need the m. How come they did not give me the m? By the way, this is a very common practice in both grade 12 and even 10 times more in first year. Say again? Actually, okay, here's the thing. Technically, you can never solve for it because you don't know it. And you actually don't have enough information ever to find out what the mass of the ball is. But I'll give you actually a very important tip here for both grade 12 and first year. Everyone, if there is a symbol in the equation that you need to calculate, that you need for the equation to be complete, yet you're not given that, this is a hint that that symbol will cancel out when you do your math. Always, if a symbol appears but is still not given, it will cancel out. Okay, here's another way to think about it. What if you're still so fixated on giving a number to the mass? Literally give it any number you want. Seriously, you can give this ball a mass of 1 nanogram, or you can give it a mass of 1 metric ton. Because when things cancel out, does it matter what number you pick? No. So to be smart, what's the easiest number we can pick? What? Okay, who said 0? If you said 0, technically you're right, but the problem with 0 is that it does what to any side it appears on? It completely kills it. We don't want the site to be killed. We want the site to be what? To be completely neutralized, which means the best mask to always use is what? No, no. One. But by the way, just so you know, when you put something as one, it's as if you did what to the two symbols? You cancel them out. Whenever something is given a value of one, does it ever appear? No, it doesn't. So whenever you're still not sure or not 100% okay with canceling them out, go ahead, give it any value you want. And the easiest value to pick is what? One. Okay? But I'm not going to do that. I'm going to do it with an unknown m to prove to you that it's going to what? It's going to what? Cancel itself out. All right? So, so let's do part A. Everyone, part A. What do I need to find at the instant when it was kicked? How many energies does it have when it was kicked? 2 energies. So everyone, let's write this. Part A. EM equals. Come on, what's EM equal to? By the way, you see I'm skipping the steps, right? Well, I'm not really skipping them. I'm still doing them, but instead of EK, EG, EM, I'm doing them in one what? In one single line. Yes. So EM is defined to be what? EK plus. You got it. Okay. Keep going. Half M. Okay. What's the speed? Might as well just plug in the numbers that we know. 12 plus M, 9.8. And what's the initial height? 22. Yeah, 22. You're right. Oh, my bad. There we go. 22. Equals. By the way, is the M going to cancel out now? No, but is it going to add up? Yeah, this is like 3x plus 5x. You collect like powers or like terms. Depends how you like to say it. Okay, what's 12 squared? Anyone? One of those famous squares? 144. Half of it is what? 144. 140. 72. So this is 72m plus 22 times 9.8. That's 220 minus 0.2, 4.4. Yep, 215.6. Also with what variable? M. You got it. 215.6 m. So what is that equal to? 72 plus 215 is 200. 0.6. 87. Still in what? In? With what variable? By the way, is that meters or just m for mass? Yes, everyone, this is times m. This is not m for meters. By the way, why can't it be meters? Why cannot it be meters? Because we are calculating what? Energy. Energy is measured in what? Joules. This is m for mass. Okay. Does EM ever change? Does the mechanical energy of an object ever change? In a system? No. Which means what? EM at the beginning is the same as EM at the top, is the same as EM right before it what? Right before it hits the ground. Yes. So right now, we're going to say what? EM. So actually, to Ammar's point, he's right. Maybe we should have what? Put another what? Comma subscript, like maybe EMI and EMF, right? EM initial and EM final. Still already knowing that EM initial and EM final are always going to be the what? Okay, so you know what? You're right. Let's make it, everyone. Let's make it EM initial. Thank you. I usually sometimes use another subset like EM top, EM bottom, just to tell myself the location of the instance. This one is EM final. What's the energy that completely goes down to 0? Gravity, which means technically this is just what? EK. So it's half. So I'm just going to write EK, which is half M VF squared. Is there any what? Sorry, say again? You're good? All right. What did we say about EM all the time? It's what? Always the same, which means what? EM initial must be equal to EM final. All right. So I'm going to equate this guy to this guy. So 287. Yes. Yeah, go ahead. 100%. Again, if this sinks in, trust me, you will never have a problem with energy conservation until you finish all the physics you ever studied. What's your question? Which line? The third one? Okay. All right. You agree that EM initial was a combination of both motion and elevation, right? Okay. It went up, which means it's still both moving and elevated, right? And then it goes down, which means it's still what? Both moving and elevated. However, right before it touches the ground, practically, what's the height? Sorry, what's the elevation? Practically 0, which means what? All of the EG now what? Seeps into which bar? The EK. So that's why I'm saying what? It's practically just the EK. Good. So 2.87.6 M equals 1/2 M VF squared. What happens to the M's now? Now they cancel out. I told you, it has to happen. By the way, this idea never fails. If you're given a symbol that doesn't that appears, but you're not given the value for, it has to cancel out. All right, so cancel, cancel. Okay, how do you solve for VF squared? Sorry, for VF. Mhm. Well, you can either say divided by half, because technically it is a 0.5, or multiply it by 2. Either way, by the way, everyone, you should know that dividing by half is the same as multiplying by what? By 2. Dividing by half is like multiplying by 2. Dividing by 2 is like multiplying by what? By half, or 50%. Always think of it this way. So whether you say, like Ahmed said 2 days ago, multiply this side by 2 to cancel the half, which means you also have to treat the equation equally and multiply this side by 2. And then you square root. So I'm just going to do this the question in one shot. So let me just squeeze this in. And I'm just going to put this back. Go ahead, you can do it. And just to verify my answer with me at the end. So that means VF equals. By the way, could my VF ever go back to 12? How come? Because it was 12, it gets to slower than 12, it gets back to what? 12, but then what happens as it goes down? It accelerates more. It accelerates, which means it builds up to a higher speed. Depending on how much elevation still needs to go down. So let's do that. So I need to 287.6. I'll show you. Divide by half will double that number. Yep. And then you square root that guy. Yeah. As long as I know that it's bigger than 12, logic stands correctly. So what's the significant situation in the whole problem? 3. So what would this be to 3, technically? 23.98, you cut it at the 9, whoops, that bumps it up. So it should be what? 24.0. Wow, almost double the speed. 24.0 meters per second. Nice. Yep. Okay. I have a question for you. Could you imagine doing that problem using kinematics? Would you rather do it with energy or kinematics? Look how easy it is with energy. How would you have done it if you did kinematics or projectile motion? You still have to find the what? The time of flight, right? Like we did. And maybe solve a quadratic equation. And then do the what? The VF on the X and the VF on the what? And then do the what? Do the Pythagorean. Lots of things happen with vectors. Are there any vectors here? That's the beauty of scalars. You just equate initial to final and you call it a day. Okay? So always know that usually energy approach is much faster and what definitely much easier than kinematics or forces. Okay, but again, we need the whole picture anyway. All right, what's the question B? What's the answer for part B? Sorry, for part A, if the initial velocity is at angle 53.1, what? Below the what? The horizontal. Okay? Okay, hold on. Hold on. Does energy, by the way, did we incorporate, everyone, did we incorporate the angle at any stage of our solution. Which means, what would you say your answer to be is? Exactly the same. By the way, question for you. It's still going to hit the ground at the same speed. But is it going to take the same amount of time to fly or a much shorter time now if you angle it down? Exactly why? Because it's not going to have to go up and then what? It's going to just go what? Straight down. Again, do you see how long it would have taken you to do it with kinematics? You still have to do another quadratic equation to solve for time and then to find the time of flight, yada, yada, all of that. Okay? So we can say what? We can say for part B, everyone, we're going to say one phrase. Since angle is irrelevant, same answer. Angle is irrelevant. What does irrelevant mean in English? Relevant means important. Irrelevant means not important. So angle is irrelevant, like no relation. Irrelevant. Same answer. By the way, same answer only for speed. How about all other things? They're different. Time is different. The distance it travels is different. The maximum height it gets to is different. Everything else is different. But the speed is the same. Okay, what's part C? Ahmed, what's part C? Sorry, say again? No, speed of hitting, speed of impact, speed of landing. The speed of landing is the same. So say that, okay, say that again. You mean part C? Oh, part B? No. Part B is, what is the answer for part A, which is the speed of the ball just before it strikes the ground, if the initial velocity was, instead of you kicked it up, you kicked it down. So we just said because the angle was not used at all in the part A, it's also not going to be used at all in part B, which means we're going to get the exact same hitting speed as well, even if you shoot it down. Where am I losing you? By the way, they're not asking for the initial speed. They're telling you, what if instead of you kicking it up, you kicked it what? You kicked it down. So it's like you actually, it's kind of like you kicking something down. It's kind of like making something slide off of what? Off of a surface, right? Because when it starts below the surface, right? So the question is saying, what if you did not kick it up? What if you kicked it this way? With how much speed is it going to hit the ground? It's going to hit with the exact same speed as when you kicked it what? When you kicked it up. But everything else is going to be different, right? It's going to take shorter time to go down. It's going to definitely travel a lesser distance. And obviously, it's not going to make it to a maximum height because the maximum height was basically the height of the roof. That's the difference in the question. What's part C, Ahmed? Okay, if there is air drag, we know for a fact that is it going to hit with the same speed as before or slower speed? Why? Because air drag is another form of what? Friction. Friction gives or steals energy from the system? Steals energy from the system. My question to you is, if it was air drag to both parts A and B, where would it hit this? Sorry, where would it hit the ground with more speed with air drag? If you kicked it up or if you kicked it down? How many people say down? Yeah, I need someone to tell me why. You're right, it is down, but why? Jinan. I'll give you a hint. Think of how long it stays in the air. As long, which means, is it gonna? Where does it experience more drag? When it's kicked up, when it's kicked down, which means it's gonna lose more energy as it travels this way. But here it's gonna what? Go straight down. So where will it hit at a higher speed, when you kick it up or kick it down? If there is air drag. If there is no air drag and vacuum isn't considered, both of them are identical. What do you want to say? Exactly. The length of the curve here is longer than the curve what? Here. And friction only acts when things are in what? Are in what? Motion, which means if you move more, you lose what? You lose more energy to air drag or friction. Perfect. So everyone, part C. How can we phrase it? If you kick it up, it travels. Sorry, it's anyone? Sure. So yeah, thank you. So with air drag, everyone, with I'm just gonna say with drag, um, uh, kicking it up leads to more time in air, so more energy lost. Done. Very good. Okay. All right. Last question for today. How many questions do we have? One, two, three. Okay, let's look at this one. Let's do this one. At the base of the hill, a sled with a rider having a combined mass of 125 kilograms travels over perfectly smooth icy hill, which means what? Smooth icy hill, no what? No friction. Okay. How far does the sled land from the foot of the hill? Okay. How are we going to do this with energy? First of all, is there motion there? Is there motion here? Is there elevation? So apparently, right there when the system started, what was the only energy relevant? EK. Okay. They start going up. So what starts happening to the two bars? Come on, everyone. They start going up. By the way, can they ever speed up as they go up? If they have no propulsion of their own. Which means what? If they go up, what happens to the speed? Because the EG bar is going what? Is going up. By the way, what if the speed was very little? Is there any guarantee they could make it to the top of the hill? Nice. Okay, so we're assuming that this speed will be able to get them to at least this height. Keep going. What's up? Oh, it's already in motion. The existent energy now is basically, again, if the energy is being lost to friction, they could technically stop right even before they get to here, right? Right? But there is no friction, which means they technically could go forever as long as they go what? Horizontally, right? However, now they start going what? Going up, which means, by the way, there is applied force on them, but it's not with them. It's what? It's against them. It's the FGX of the FG component, right? Yeah, but you're asking what still drives them, right? It's the initial energy of the system. Okay? Yes. Well, okay. So we're assuming basically what that the contact force or the contact is always gonna be maintained until it reaches here and here. Ooh, that's the whole question. So the question basically what starts as energy, but then kind of goes into what kind of motion? Projectile motion. Okay? No, no, but you're right. I mean, okay, you're saying that they go and then they loop. That's basically what they're saying. Yes, but it depends on also what? On like how much, like what kind of angle are you actually what pushing against the what? Pushing against the hill. You see what I mean? We're assuming there's no what? The only force against the hill is just the normal force, like this. That's all. Okay? All right. So what's the only energy here? Come on, everyone. What's the only energy here? EK. So EK equals something, but EG equals what? 0. Okay. Do I really care what happens here? Not really. I know what happens. EK goes down, EG goes up. That's fine. Right here, I know that EG is what? Is not what? Which means I'm just going to put a number, equals to a number. I have a question for you. What if EK here is equal to 0? Are they ever going to jump off the hill? No, they won't. They basically come to a stop. Apparently, by the way, there's no guarantee, but the question is saying what? How far does the sled land from the foot of the cliff? Which means what? Apparently, they're still going to have a little bit of a speed here to make them what? To make them jump, to make them basically cross the cliff. So here, EK is also another what? But what is always what's always maintained at the same value? EK, EG, or EM? EM, which means the addition of these two, which technically only happens to be what? Must be the addition also of these two. All right. So let's do that. So step one, everyone. Step one. Step number one. EM initial must equal what? EM what? Oh, yeah, I'm setting up the equation first. Everyone, I'm following a different approach now. I am setting up the equation of what? Of EM being itself, being equal to itself all the time. Okay, initially, what was EM? According to the diagram I just showed you. Initially, what was the only relevant energy for EM? EK. So go ahead. So half M V initial squared equals. Technically, how many energies do we have right before they jump? 2. EG from elevation and EK from still some speed left. So here would be what? MGH plus half MVF squared. Did they give me the mass of the combined sled and person? Do I really need it? Nice. Could I cancel it every single time? You see, it's weird. Sometimes they don't give it to you and you still cancel, and sometimes they actually what? Give you the number and you can simplify your math but not even using it. As long as it appears everywhere. All right, so cancel, cancel, cancel. Do I know the VI at the base of the hill? Do I know? Yeah, I do. 22.5. Do I know the height of the hill? Like at the very end, the height, 11 meters. What can I calculate here? Or sorry, what can I solve for? Exactly. I need to know their speed final for the what? For the hill, which becomes the initial speed for the jump. All right. Let's solve. So 1/2. Sorry, in purple as well. 1/2. VI was 22.5. 22.5 squared equals 9.8 times. You said 11. 11 plus 1/2 VF squared. Okay. Let's solve this. How do you solve it? You really just need to clean up. You need to clean this up. You need to clean this up and move it here, and then multiply by 2 and square root. Okay, I'm going to do the whole thing in one shot. VF equals. Go ahead. I'll just squeeze this a little bit to give myself more space, and then I'll catch up with you. Anyone got a number? I'll do it. So okay, so that's the left side. And then I'm going to minus 9.8 times 11. So minus, open a bracket, 9.8 times 11. That will be multiplied by 2 and square rooted. So, or divided by half, whichever way you want to think of it now. And then square root. Boom. Their speed right before the jump, right before they clear off, is 17.05. 17.05 meters per second. Noura, what's the question asking for? Like eventually, what's the question asking for? How far means what? Distance. Can I use energy to solve for distance? No. I don't have EK equals half mv squared, EG equals mgh. So energy doesn't help me anymore. I need projectile motion. I need projectile motion. All right. What do I need to do with projectile motion? Everyone, how many equations do I have with projectile motion? Two. There's one for delta dy, and there's one for delta dx. The problem is I can't use the delta dx one, which is technically what I want to find. I need to solve delta dy first. So, step number 2. Okay, everyone, here's the delta dy equation. Delta dy equals vi. Remember, delta dy equals vi y delta t minus 4.9 delta t squared. Okay, I know you're starting to get concerned and go, oh crap, a quadratic? Actually, no. Question for you: did they jump at an angle or horizontally? What's the most amazing thing about a horizontal jump? What's the angle? 0, which means no y component for the initial jumping speed. That is a 0. This will happen every time you have a horizontal jump. Every time. Great. What's delta dy though? How much distance do they go down? They go down as much as they went up. How much did they go up? 11. So how much did they go down? Exactly, negative 11. Remember, with delta dy equation, if you're going down, if your final level is lower than your initial level, your displacement is negative. So negative 11. Nice. Many people would have forgotten that, especially after like 2 months of doing kinematics. Equals what? Negative 4.9 delta t squared. And by the way, Jinan would tell you, if you forgot the minus here, can you ever square root a negative number? No, because you gotta be like, oh, wait a minute, 11 by negative 4.9 is negative. I can't square root. I forgot the negative. Nice. So what's my delta t time for flying? Well, let's divide and square root. The good news is negative will cancel the negative. So 11 divided by 4.9, and then you square root. It will land almost after 1.5 seconds, which is what I'm going to do anyway if I round it up to here. So 1.50 seconds. Now what equation do I use? I've already, the delta dy is done. Delta dx is the last thing you need. So delta dx. What's the equation for delta dx? Only what? Vix delta t. No acceleration on the horizontal. Gravity only pulls down. So equals Vix delta t. Do you remember what's Vix? It's Vi cosine of theta. But what's theta for a horizontal jump? 0 as a degree, which means what? Cosine of 0 is 1. Perfect. So, and what was the horizontal jump speed? Yes, the 17.05, not the old 22.5. That was at the base. So 1705 times 1.5 second in the air times cosine of 0, which is really a positive 1. So apparently they would land at this distance. 1705 times 1.5 distance in the air. They would land at 25.6 meters off the cliff.